Here in this part, we learn how to prepare optimum capsules. And in this particular example, we'll focus on hard gelatin capsule filling optimization. So basically, we find what are the best or the classical independent variables and what are the tests needed to assess the capsules, which are the dependent variables. So what is a capsule? There are two types of capsules, which are the hard gelatin capsules, and this is basically the two parts that we're all familiar with. And you could have soft capsules, which come as one part. This is often used for oils or other liquids or semi-solids. The most common one is the hard capsule, which is the two pieces. And this is filled with powders or pellets or granules. Um, the shell made for the hard capsule is made from gelatin if it's animal source or hydroxypropyl methyl cellulose if it's vegetarian or from vegetable source. It is easy to swallow, and then what happens, the shell will dissolve in the stomach, allowing the content to dissolve. It can be used to mask the taste of drugs, and it come in different sizes. So from 000, that's the biggest size, and you can go all the way to the very small size to 5, which is on this scale is considered the smallest. Capsules, they come in different sizes, and as you can see here in this diagram, you start with the biggest one, which is the 000, that is 1.37 milliliter. And then as you see here, is the numbering goes from 00 to 0, which got 0.91, size 0, and that goes a smaller volume, and that gets smaller and smaller until you get the smallest size, which is size 5. Those are used depending on the application. So, for example, size 3 is used in inhalation in products. 000 and 00 is used in veterinary application. So for treat animal conditions, for animals. The size 0 and 1 are commonly used by adults. So for the most classical one, size 2 and 3 is for children or pediatric patients. And like I said here, the inhalation products often, the dry powder inhaler devices, they use size 3, in many cases size 3 capsules. And then you could have size 4 and 5, and this is very low dose or low dose medications because of the capacity of the capsules. The process of filling capsules are more or less intuitive. So you start with the capsule separation, powder filling, and finally capsule closing. This process, of course, is automated, but then if you want to compare how you make capsules compared to other dosage forms like tablets, then this is considered more complex compared to tablets because there are 3 steps here: capsule separation, filling, and then closing. While with tablets, once the powder is mixed, then the process is just pressing the tablet. So it's only one process to produce the dosage forms. The key challenge when filling capsules, you probably can imagine that, which is the powder flow. And the reason here, because powder must flow easily into the capsule shell. If there is a poor flow of the powder, that means there will be uneven fill weights and therefore there will be wrong dose. And of course, that will be very serious issue. Things which can affect the flow are the particle size, the shape of the particles, and the moisture content. Particle size, of course, because bigger or smaller particles, they often adhere to the walls or to the surfaces, and therefore makes the flow harder. And the shape of the particles, because if the particles are uneven, then that will make the flow harder. And likewise for moisture, because they will clump together and reduce the flowability. Sometimes what can be done to improve the flow is the use of glidants. Glidants such as silica, and that basically to reduce the friction between the particles. And another strategy which can be used is use a lubricant. And this is what we mentioned earlier with the tablets, which we said that lubricants are used because they can coat the surface of the powder, and that means they can help with reducing the friction, and therefore they help the powder to slip. Classical example or common example is magnesium stearate. One of the dependent variables we commonly use when making tablets is Carr's index. And the idea of this is to make sure the powder flows well. And as mentioned before, larger particles, they flow better. However, they will have low dissolution, which is a problem for drugs because you want them to dissolve faster. So one thing, as you can see here in this animation, is to use particle size reduction. And the idea here, you can see a distribution of the particle size, so you can get a shift in the particle size distribution. The way you check that your powder is still flowing well, but of course you manage to reduce the size to a range that will dissolve okay, then using this Carr's index. And that can be represented using this relationship. So you get the relationship between the tap density minus the bulk density divided by the tap density multiplied by 100%. If you get a ratio below 15%, that means you get excellent flow. And then you get this comparison whether between 20, 35, 12, and that just gives you an idea about how good is the flow. If you get a ratio which is above 35%, that indicates very poor flow. Basically, you can tell this because of the density. So the tapped means you take the cylinder, graduated cylinder, and you tap it at constant number of um, repeats, and that will reduce the volume. And the more difference is from the bulk density, then that means the particles, they will be just filling much more of the voids, and that affects the flowability or the index of the, which indicates how well the particles flow. The question is, what variables can we change? So we mentioned before about the glidant concentration, and we said that helps with the flow. So a low value, for example, can be as low as 0.5, and then the medium is 1, and the high is 2%. The other variable which we can change is the mean particle size. And here that we measure or we choose three different sizes, 50 micron, 100 micron, and the high range is 200 micron. Bigger particles flow better, but may dissolve slower. Among the different dependent variables that can be used to assess the quality of capsules is the disintegration of the capsule shell. Although in capsules is not very common as in tablets to assess disintegration. And the reason for that, because this is almost more or less similar. So for example, in many cases gelatin capsules are used. So the time that that allows the tablet to dissolve is more or less similar. In some cases that could be changed depending on the nature of the loaded drug. So but that is very important step before dissolution can start. The process of dissolution of the shell is followed by the process of dissolution of the capsule shell and the process of the drug release from inside the capsule. So what happens here? We measure the amount of the drug that is released per unit time. And as mentioned before, in the tablets optimization part, the same thing happens here. So there is a pharmacopoeial standard to specify the time that should, by then, the drug is dissolved. The quality of the capsules follow some more or less similar kind of tests. So one important test we do is the full weight. Then the way this is done is by weighing 20 capsules, and we check the uniformity across all the assessed tablets. The other thing is the disintegration, and this is the time required for the shell to rupture. This followed by dissolution, that's basically the person's drug released over versus time. The for the content uniformity, basically we want to know the tablets they have the same amount um, of the drug, for example. So you need to ensure there is no variance, a significant variance among the capsule, and this is basically done through measuring 10 individual capsules. All tests ensure every capsule basically gives the right dose. The results that we can get from capsules are related to how the variables interact with each other. So for example, when you increase the amount of a glidant, and we said this is used to improve the flow of the powder, that means it will also help with the uniformity of the weight content, so how uniform the weight across all samples. If we increase the particle size, that also can increase the flow. But on the other hand, it can slow the dissolution. So if we have too much of the glidant, can slow drug release. And then the fact there should be some kind of interaction. So potentially that will lead to a dependence of particle size on the glidant level. So basically what that means, if you increase the particle size, that will be, or the effect of particle size, that will be related to the glidant level. And that means the way we assess this is we do a counter plot for each test, for each dependent variable test. And then what we do is overlay. So as you can see here on this image on the right, we overlay the contour plots or the maps for each dependent variable. And then we look for the common part just to find that is the optimum region that will have the best properties. So that will also give us, when we get the equation of the model that we've been using, that will give us an idea about the interaction that can happen between the variables.